Welcome back. So in this video, as you can see, we're just going to have a quick revision of Unit 1. When I say quick, I mean hopefully I'll keep this under 1 hour. Now, if we think, Unit 1, this should probably be about 12 hours, right? The whole content, that's how many teaching hours are recommended. So of course, yeah, I'm not going to be able to fit in, everything here in this 1 hour. Although hopefully I will cover about sort of 80 to 90% right, of what they commonly ask. Now, if you haven't learned this content before, then I would, well, I guess, yeah, either just read the book, or of course, watch other videos on YouTube. If you've never learned this before, then honestly, this video is not going to be enough. But if you just want to sort of, recap, right, if it's maybe, I don't know, let's say the night before your test, then yeah, hopefully this video will be kind of useful revision. Right, so if we just look at everything we need to know then, I'm not going to read that, but if you want to pause the video, I would say you can use this as a checklist, kind of at the end of the video as well, right, just to make sure that you kind of know and understand all of this. So first, I think, okay, right, if you watch the previous videos, we talked about binary, we said that's base 2, and we say in a computer where everything is going to be binary, right, whether that's numbers, text, audio, images, videos, images, programs, where of course everything is stored as binary. Right, then there's going to be Denary, so of course Denary base 10, and this is just what people use in day-to-day life. And of course, when we say base 10, right, that means there's 10 digits available. Of course, 0 to 9. Right, base 2, of course, 2 digits. Right, then finally, the one you need to know is going to be base 16 or hexadecimal. Of course, that's 16 digits. 0 to F. Okay, so I think this one we will look at in more detail in a minute. Right, we say the common use cases were IP version 6. Also MAC addresses, HTML color codes, right, memory addresses, error codes. And the advantage, right, is going to be shorter or easier, right, way of representing binary values on paper. Because if you remember what that, one hexadecimal character is going to be 4 bits, right, therefore, of course, it's just going to be shorter. Right, so if we say a bit, right, that's one binary digit, right, a nibble, maybe some people have forgot this, right, that's 4 bits. And then a byte, I think, hopefully people should remember this, right, it's quite common, of course, just 8 bits. Right, then we say, the most significant bit, or MSB, basically, that's going to be the leftmost bit, right, the bit with the highest value. Right, then in contrast, the least significant bit, or LSB, that's going to be this one here, right, the rightmost, or the bit with the lowest value. And of course, if we just look at the other values, of course, right, it's just going to double if we go left, so 2, 4, 8, 16, and of course, it's going to half if we go right. Right, so if we have some practice, converting from binary to denary. So if we look at this one, of course, right here, there's no 28s, right, there will be a 64. Right, there's also a 16, so 64 plus 16 is going to be 80. Plus 8, right, 88. I guess plus 2, right, that should just be 90. Now, I think, let's see this other one, right, I'm not going to do, but you can pause the video, right, have a go. Just in the interest of keeping the video shorter. Right, so if you've had a go at that, then you should get 235. Of course, just add up all those numbers, right? Check that's correct. Now let's look at some formulas for calculating the maximum range and number of unique values for unsigned numbers. So first then we want to think, what's the formula for the number of unique values? So let's say if we've got 10 bits. Well, right, what's going to be the formula for telling us how many unique values that we can represent with 10 bits? Right, so hopefully people remember that's going to be 2 to the power of n. And of course, if we're saying 10, 2 to the power of 10 is going to be 1024. Right, the next one, so what's going to be the formula for the maximum? And note here, right, currently we're only talking about the unsigned maximum. So hopefully people know this, it's going to be 2 to the power of n minus 1. So of course with 10 bits, it's going to be 1023. Right, then finally, the range. So if we're thinking unsigned, of course the smallest can be 0. And of course, the maximum is just, this maximum here. Right. Now, the thing to note is that, of course, these formulas work for any base, just change the 2 to the new base. So if you want to say, I don't know, let's say base 16, we want to calculate what's the biggest number that we can represent with, let's say 8 hexadecimal digits. Then, of course, it's just going to be that. And I don't know, that's going to equal, right, whatever it equals. And if we think, why does the range formula, and also why does the maximum formula contain the minus 1? And of course, that's because we're also counting 0. So if you think, let's say we have, 2 bits. Of course, 2 bits, we've got 0, 0, right, then 0, 1, right, 1, 0, and 1, 1, which of course, this is going to be 0, this is going to be 3. So if we think, of course, right, that's 4 different numbers, but the maximum is going to be 3. That's of course, because 0 is going to be one of these numbers. Then let's just try going the other way from denary to binary. So the first one, 75, of course, right, 1 to 8 is too big, that's going to be a 0. Alright, there will be a 64, alright, well there won't be a 32, and of course, right, if we have 64, well then we're going to need 11 remaining. So of course, well 16 is bigger than 11, right, but then here, well there will be an 8, alright, that's going to give us 3 remaining. Then of course, well, to make 3, just a 2 and a 1. Right, now if we want 148, now I think this one I won't do, although quickly you can probably see what it's going to be 128 and then just plus 20. So I suppose what 20 is going to be 16 and 4. Right, then if we think about the redundant bits, so if we're talking about positive numbers, well then, yeah, okay, I guess we can say that any leading 0 is going to be redundant. Now, right, this is if it's unsigned. If it's signed, then I guess, well, yeah, okay, so for signed, of course, we will need 1 0 still. Otherwise, like, if we don't have this 1 0, well then, of course, well, it's going to be minus 2 plus 1, which is going to equal minus 1. But yeah, I guess the kind of extra, I guess kind of the extra leading 0 is going to be redundant. Right, and then for negative numbers, I mean, well, it's just the same, but it's going to be leading 1s. So in this case, we can say, what, this one, which if we think about that, well, it's going to be minus 8, right? There won't be a 4, there will be a 2, there will be a 1. So what, that's going to be minus 5. That's, of course, well, this one is minus 5. Right, but then, yeah, this one is also minus 5. So, of course, yeah, these are, okay, these leading 1s are just redundant. Right, then if we look at how we calculate the required number of bits, so, well, the rule, okay, if the target number is greater than the current binary positional value, but less than the next, then we need this number of bits. Effectively, that's just saying, right, and I guess alternatively, if you have a calculator, what use this, say the ceiling of, well, log base 2 of n. But if we say this one, effectively what this is saying is, it's just saying we'll get the position that's kind of, like kind of in the middle. So if, for example, we want 70, well, 70 is going to be here, right? Since, well, of course, it's bigger than 64, but less than 128, right? Therefore, well, we're going to need this, which is what, well, of course, that's going to be 7 bits. So if we think 56, well, 56, well, it's going to be bigger than 32, less than 64, right? Therefore, we're going to need 6 bits. And of course, yeah, well, it's going to be 2 to the power of 5, right? Or 6 bits in total. Right, if we do the same logic with 127, well, of course, 127, it's going to be here. So, of course, well, that's going to be, well, 7 bits. Right, if we try 128, well, now 128 is going to be this one. So, of course, well, here, right, we're going to need 8 bits. Since, yeah, if we only have these, right, that's only going to give us 127. And remember the rule that we say, right, right, let's say if we take any number, and then if we take all of the values right of it, well, all of those values, they're going to sum to 1 less, right, than this kind of, left number. So here we say, well, this is 32. Right, but then if we sum, well, 16 plus 8 plus 4 plus 2 plus 1, right, that's going to equal 1 less, or 31. Right, likewise, if we take 8, well, all of the numbers to the right of 8 are going to be 1 less than 8, right, or, well, of course, just 7. Then if we look at hexadecimal, well, here we can see the table, of course, what hex, denary, and binary, just the equivalent values. So hexadecimal, well, it's base 16. The first 10 hex digits are easy, right, just the numbers 0 to 9. Right, the next 6, well, the letters A to F, yeah, I think people should know this. Right, an example of a valid hexadecimal, and in exams they often ask these kind of questions. Right, so well 9D4, because of course well all of these digits, right, they're all in the range of 0 to 9, A to F. Right, invalid, well here because of of course this G, right, so this G is bigger than F. Right, then if we look at converting, so what this is going to be from hexadecimal to binary. Then I guess what we do, well, we're just going to say, well, of course A is just going to be 10, right, so 10 in binary is just going to be that. Of course, well, 4 is just 4 in binary, right, that. Obviously, yes, 7 here, right, and then what E, and of course, what E is going to be 14, right, so 14 in binary is just this. And so, well, of course, not only does this work going from hexadecimal to binary, but we can also use this, right, going from binary to hexadecimal. So, of course, just breaking the binary into, 4-bit nibbles, right, then just converting each nibble, right, into the equivalent hexadecimal character. Right, so, well, again, right, that's going to be the positional values, what binary and hex compared. Then if we look at the relationship, well, we say that, I guess if we look at here, well, of course, right, 1 and then 4, right, 2 and 8, 3 and 12. So, of course, it's going to be multiplied by 4. The difference between the, between the base 16 power, right, and the base 2 power. Right, so because of this, and, well, I guess here because we say, 2 to the power of 4 equals 16, right, that's going to be why 1 hex digit equals 4 bits, and of course, why 4 bits equals 1 hex digit. Right, if we have practice, and again, I'm just going to do the first one, you can pause the video, have a go at the other two, right, just to keep the video shorter. So, well, 3, 2, and, right, so the thing to note, right, okay, this is hexadecimal 3, 2. So sometimes they might write that, you know, with a kind of subscript 16. So what we're saying is, well, of course, right, we've got 3 times 16, which is going to be 48, and then, well, plus 1 times 2, which, well, of course, that's going to be 50. And again, right, if you want, just pause the video, have a go at the other two. Now, FF you should know because, well, that's 255, right, but of course it's just 8 ones. Then, well, this ABCD, yeah, I mean, that's going to be complex. Right, I guess it's probably going to be this. Right, then if we look at going the other way, so, well, of course, well, here it's Denary. So we want to think, well, how many... okay, right, so if we think, well, of course, 256 is too big, right, so there's, well, 0, 256. But then we want to think, well, of course, yeah, okay, so, right, of course, there are going to be some 16s. And we want to think, well, how many times can we, how many times can we divide 45 by 16? Well, yeah, how many times can we kind of wholly divide 45 by 16? So what that's going to be, I think, right, that's going to be 2. Because if we try and divide it 3 times, I guess what 3 times 16 is going to be 48. Yeah, whereas if we go 2, well, that's going to be, what, 32. And then, well, of course, that's going to give us 13 remaining. So 13, well, everything, well, of course, well, A is going to be 10, right, B is 11, C is 12, right, therefore, well, D is going to be 13. Yeah, and well, like, okay, right, let's say if people are confused about that, of course, what we're saying is, well, yeah, of course, well, it's 2 times 16, right, well, plus 1 times D, and of course, well, D is 13. Alright, so again, like, okay, so I'm not going to do the others, but again, you can pause the video, right, if you want to have a go. So this one, right, it's just going to be F7 because, well, I think F times 16, right, that's going to be 240 because, well, 15 times 16, right, then, of course, just plus 7. Right, then this last one, I mean, yeah, that's going to be quite complex. Right, then if we look at hex to binary, so again, let's just do the first one. So, of course, well, 7, right, in binary, well, 7 is just, yeah, 3 ones like that. Right, of course, well, 4 is just, well, yeah, no 8s, right, then 4. Right, and then B, so B is going to be 11. So that's going to be, what, 8, right? There won't be a 4, there will be a 2, there will be a 1. Alright, and then I guess you can also try these others. So again, pause the video, have a go if you want. Yeah, and you know, again, I mean, this one should be quite easy because, what, D, so D is going to be 13, I think we said, right? E is going to be 14, A is going to be 10. Well, then, of course, just another D. And yeah, I guess, right, the other one, not too difficult. Right, then let's go the other way, so binary to hexadecimal. Right, so if we see, well, 4 ones, I mean, 4 ones, hopefully you can just remember, alright, that's going to be F. Well, okay, right, zeros, well, that's going to be, well, 0. Right, well, another 0. Right, then here, well, that's 8 plus 4, right, that's 12, plus 1, right, that's 13. And again, we saw, well, of course, right, A is 0. Okay, sorry, yeah, A is 10, B 11, C 12. Therefore, well, D is going to be, yeah, 13. Right, and then, again, so, of course, yeah, these ones have a go yourself. Right, then if we move on to the different types of numbers, so 1 is going to be an integer, and an integer, well, that's just a whole number, e.g. 3. Right, then there's going to be a real, so that's going to include a decimal point, right, e.g. 3.1 or, you know, 3.0. Now, of course, these are going to be equivalent, right? If we say, well, 3 integer, right, well, that's, of course, yeah, equal to, you know, 3.0, yeah, the real number. Right, then I guess, well, unsigned we mentioned, that's positive only, so we say, yeah, all bits are going to have, you know, positive values. Right, and then signed, well, this can be positive or negative, and we say, what, the first bit is negative. Or I suppose when we say first bit, probably, well, MSB, right, the most significant bit is negative. And of course, yeah, this is also just 2's complement. Right, then if we look at the quantities, right, so, yeah, okay, well, alright, so when it says for computer science, like, this is saying in comparison to, you know, physics or maths, because, you know, physics, well, maybe you also want sort of micro, nano, yeah, other things. But for A level, right, I mean, yeah, these are the ones you need to know. And of course, well, Tera, right, 10 to the 12, Giga, 10 to the 9, right, Mega, well, 10 to the 6, and, well, Kilo, right, 10 to the 3. And of course, yeah, well, 1,000, right, going up to, what, a million, a billion, and a trillion. Right, then if we, yeah, okay, alright, so, well, then if we look at base 2, because, well, everything computers operate in base 2, then the following units were also introduced. So, well, here what we're going Kibi. So Kibi is, well, yeah, 2 times 10. Okay, oh, sorry, yeah, okay, right, 2 to the power of 10, which was the value 1024. Right, and of course we can also write that just, well, 1024 to the power of 1. Right, then of course, well, Mebi, right, 2 to the 20, 2 to the 30, 2 to the 40. So of course, well, here it's just going up in 10 each time. Right, then if we look at it, well, in terms of sort of the power of 1024, well, of course, Kibi is, what, 1024 to the power of 1. Right, Mebi is, well, 1024 squared, right, then Gibi is cubed, and, well, Tebi, right, that's, yeah, to the power of 4. And the thing that, of course, we can notice, we say, well, Kibi is going to be 1024 bytes, right? But then Mebi is going to be, what, 1024 Kibi bytes, right? Gibi, what, 1024 Mebi bytes, and what, Tebi, right, 1024 Gibi bytes. And again, that's because of this relationship here. Right, so let's try a question. Right, an MP3 file is 18 megabytes. Right, how many bits is that? So let's think then, well, if we want to do 18, right, then we just want to times it by a million. So in fact, right, I'm just going to write 10 to the power of 6. Right, well then, okay, yeah, so if we want bits, well, since this is bytes, of course, then we just need to multiply by 8. And yeah, that should be, right, okay, so it's going to be, what, 144 million bits. Right, let's try the next one. And right, an HD MP4 movie averages 4 megabits per second. How many gigabytes would a 2-hour movie use? Right, so here then you want to think, well, 4 megabits per second. I guess what then we just want to, so what? Okay, what I'm thinking is if we just convert into bits, and then once we've converted into bits, well, then we can 1 divide by 8 to get this, and also Gibi, that's going to be what 2 to the power of 30. So yeah, okay, what I'm going to do, I'm going to calculate the number of bits for the entire 2-hour movie. So well, that's 4, right? Then we're going to times by I guess hang on, okay, right, times by 10 to the power of 6. Right, then we just want to do what? So okay, right, okay. So this will be the number of bits for 1 second, right? But then if we do times 60, that'll get us for 1 minute, right? Times 60 again, 1 hour, right? Times 2, well, that's going to be 2 hours, right? Then then we just want to divide by 8, right? That'll get us from bits into bytes, and then we'll also divide by 2 to the power of 30, yeah, just to get us Gibi. Right, and then I suppose if we do all of that, yeah, that should just get us this answer here. Right, okay, yeah, I think that was duplicated for some reason. Right, then if we look at negative numbers, right, there's going to be 3 ways to represent negative numbers. Well, one is signed magnitude, and actually I do notice that in the syllabus they don't specifically mention this. Now, I think I've seen this on the previous papers. I mean, it's, well, yeah, of course, it's definitely in the book. Although, yeah, honestly, they kind of rarely ask about these. So our signed magnitude, 1's complement, it's pretty rare. But I mean, 2's complement, well, that's going to be like 99% of papers. They're always going to ask about 2's complement. And I guess, yeah, okay, I mean, probably, well, of course, yeah, the reason the exam, of course, right, always ask about 2's complement is because, well, that's just what modern devices are going to use, right? Computers, laptops, phones, tablets. Yeah, I mean, okay, well, let's say all of them are going to use 2's complement. Right, so if we first look at sign magnitude, this is kind of the simplest methods for humans to understand because, well, the most significant bit is simply the sign bit. If it's 0, it's positive. If it's 1, it's negative. So let's say if we want to represent 6, well, okay, right, this is going to be 4, this is 2, this is 1, and then, well, this is just the sign, right, plus or minus. So, of course, to represent 6, well, 4 plus 2 is 6. All right, then if we want positive 6, well, we just set this as 0. Now, if we want negative 6, well, again, right, 4 plus 2 is 6. All right, then just, set the bit to 1, right, to make it negative. Now, while this is simple, right, of course, there's a problem, and, well, one of the problems is the arithmetic doesn't work. There's also another problem that, of course, we have 2 representations of 0. One is going to be like this, right, so this is kind of positive 0, but then if you think, well, of course, this is also 0, right, but if we make it 1, yeah, this is kind of like negative 0. And because of this, well, yeah, this is one reason why the arithmetic doesn't work. Right, so if we look at some questions, yeah, I guess, well, maybe just try this one, right? It should be quite simple. So, of course, we're 7, which is going to be 4, then a 2, then a 1. Right, to make it positive, well, we're just going to have 0. Right, then, well, of course, to make it negative, well, it's going to be the same, right? But then, of course, just make that 1. Right, again, pause the video, have a go at the other 2 if you want. Alright, so yeah, hopefully they're not too difficult. Right, then if we look at 1's complement, so, okay, well, we saw sign magnitude has 2 issues, right? Of course, one of them, well, of course, yeah, okay, so one is that it has 2 representations of 0. Right, one is that, well, of course, yeah, the arithmetic doesn't work. Right, so another approach, 1's complement, was developed to try and solve this. What this means, well, just flipping, inverting, or negating the bits, right, to convert from positive to negative, right, and also vice versa, right, negative to positive. So, for example, if 5 is going to be this, well, of course, well, yeah, 8, 4, 2, 1, that's, of course, well, just a 4 and a 1, right, well, then we're just going to invert those. So, negative 5, well, of course, right, this 0 becomes a 1, right, this 1 becomes 0, yeah, 0 becomes a 1, and, well, 1 becomes 0. So, yeah, I mean, literally just, flip the bits. Right, so here there's actually no sign bit, right, and all bits contribute to the magnitude. Now, if you want to try this, well, okay, let's say positive 3. So positive, okay, well, there's not going to be an 8, there's not going to be 4, right, there will be a 2, there will be a 1, right, then of course, well, to get -3, what is just going to be flip the bits. So yeah, 1, 1, 0, 0. And again, right, just have a go at these. Right, so then finally, if we do 2's complement, and if we just say quickly, right, 1's complement has the same issue as sign magnitude, that, well, 1, the arithmetic doesn't work, and also there's 2 representations of 0. Because if we think, well, of course, well, 0, 0, 0, 0, right, that's 0. But then if we flip the bits, well, 1, 1, 1, 1, right, I mean, this is kind of -0, and yeah, this is kind of +0. Right, so 2's complement, well, again, right, this is what, basically 100% of modern computers is going to use. Right, this approach works by making the most significant bit negative, right, for example, with 4 bits, well, I guess you represent like this. So of course, right, well, now this one becomes -8 rather than +8. So to represent 5, well, it's just going to be a 4 and a 1. But then to represent a negative number, well, of course, right, the first bit is always going to be a 1 if it's a negative number. And then we think, well, okay, so now we're on -8, right, then to get back to -5, we just want like +2, +1. And yeah, that's going to get us back to -5. And yeah, I suppose, well, here you can see that, although hopefully people know this already. Right, then we just have some practice. So, well, -7, right, of course, well, we're going to want a -8. Right, well, there's not going to be a 4, there's not going to be a 2, but then I guess there will be a 1, right, because if we think, well, -8 plus 1, right, it's going to equal -7. And again, of course, just, have a go at these. Now, if you remember, there is also another way to do it, and like if we want, like, okay, so let's say we can calculate the positive number, right, then we can convert it to 1's complement. And well, if you remember, of course, right, convert to 1's complement, well, that just means flip the bits, right? Then if we just add 1, right, that's going to be one way to do it. There are actually another couple of ways as well. Although, yeah, I guess they're a little bit more niche. It's maybe a bit more difficult to show you workings, right? But I guess if you have a go at these, well, these should be the answers you get. Right. So if we look at, well, yeah, convert from positive to negative, and I think we've kind of done this. So if we want to convert from 12 to -12, well, of course, then we're going to need 5 bits because, well, we're going to need this -16. Right, so, yeah, and okay, well, of course, right, this is going to be the flip the bits and add 1 method. So, well, positive 12 is here, right, then we flip the bits to get this, right, now we need to add 1. So if we add 1, well, of course, yeah, this is our 1 here, of course, this is 1, well, then we're just going to add it. Now, I think I'm not going to do the addition because, well, we'll look at addition probably next. But yeah, I guess if you add that, right, then you should get this. And of course, this is going to be really easy to verify because, well, here we say, well, this is -16, right, this is going to be a 4. So if we just plus that, well, -16 plus 4, well, of course, right, that's going to be -12. And of course, well, yeah, that's, correctly converted our positive 12 into -12. Right, so, and then, well, okay, all right, so here's just some practice. So, 17 to -17, right, try these. And, right, if you try those, then, yeah, these should be the answers you get. Right, so just to sum up all of that, well, sign magnitude and 1's complement, again, they both have the 2 representations of 0. As a result, the arithmetic doesn't work well. I mean, it is possible to do arithmetic, but yeah, the circuits are going to get more complex. There's more kind of weird edge cases, right? So it's going to be slower. Right, in contrast, if we look at 2's complement, well, the negative values are going to be +1 compared to the 1's complement, which, yeah, I think we can see here, right? So if we take the equivalent 1's complement, right, it's always going to be 1 down, or, +1 compared to that. And of course, well, that's why we need to flip the bits and add 1. Right, there's also only 1 0, which is a good thing. Yeah, we don't have this -0. And we also get the additional -8. Whereas, of course, if we look at here, so yeah, obviously looking at these two, right, we don't have this -8 here. And again, well, of course, that's because we have this, extra -0. Then if we look at the ranges for, well, sign magnitude 1's complement and 2's complement, right, for sign magnitude, the biggest number we can represent, well, of course, right here we're going to want all 1s, okay, because, well, this is the magnitude. So because, well, yeah, of course, right, okay, we want the biggest magnitude possible. Right, but then, of course, well, the sign bit we want to be 0, right, to make it positive. If we do that, well, it's going to be 127. Right, then we look at, well, sign magnitude smallest. Again, well, of course, we're going to want the magnitude to be as big as possible, right, but then just make the sign bit negative. Of course, well, to get -127. Then if we look at the range, well, we can say, well, it's going to be plus or minus 2 to the power m minus 1, and then just -1 here. And if we notice that, well, of course, for sign magnitude, right, and 1's complement, well, of course, yeah, I mean, well, they're just going to be equal, right, it's the same formula. So 1's complement biggest, actually, this is the same as sign magnitude biggest. And that's because, well, if we think, well, of course, right, this is going to be 127, yeah, otherwise, this is going to be negative. Right, then if we just want to, well, okay, if we want to make it the smallest, we're just going to invert them. So, well, that's going to be, yeah, 1, well, then of course, yeah, just flipping all these bits, right, it's going to get us to minus 127. Right, then if we look at 2's complement, well, of course, 2's complement, right, we're not going to want this negative number, but then, well, of course, yeah, we will want all the positive numbers, right, gets us to, well, 127, or I guess, yeah, positive bits. Right, and then, well, of course, the smallest, well, I mean, right, in this case, all we're going to want is just the negative bit. Then, of course, well, yeah, all of the positives should be off. Right, that's going to get us minus 128. Right, then here, well, it's going to be slightly different. Of course, what the smallest number, what, minus 2 to the power of n, right, minus 1. Right, and then, well, the biggest, what, 2 to the power of n minus 1, and then, yeah, just minus 1 here. Since, of course, well, this goes to minus 128, but, yeah, this only goes to 127. Right, yeah, hence the minus 1 for the biggest. Right, then if we look at addition, and I guess here, what if we have what 0 plus 0, we have what sum of 0, carry of 0, 0 plus 1, right, or 1 plus 0, what is going to be sum of 1, carry of 0, yeah, 1 plus 1, well, I mean, okay, if we think, well, of course, right, this is going to be 2, now, of course, well, 2 in binary is going to be written as 1, 0, and I suppose, well, if we have a carry of 1 and a sum of 0, right, it's kind of like in this column, right, so if this is column 1, this is column 2, then of course, yeah, what we're going to have a 0 here in this sort of, you know, 1 column. Then, well, of course, yeah, a 1 is going to carry over into this 2's column. So yeah, that's why, well, okay, 1 plus 1, right, it's going to be what, a sum of 0, right, carry of 1. Alright, then if we have 3 1s, well, of course, what, a sum of 1 and then a carry of 1. Because if we think in that case, well, here, I mean, what, 2 plus 1 is going to be 3. So we have, we have a 1 in the 2's column, and of course, yeah, also a 1 in the 1's column, right, to give us 3. Right, and then I think, I mean, yeah, that's kind of saying what we said. Yeah, I mean, I guess if you want, you can read this, right? I think, yeah, again, you know, in the interest of keeping the video short, right, let's just skip this. It says if 2's complement numbers are added and they both have the same sign, right, either both positive or both negative, then overflow occurs if and only if the result has the opposite sign. Overflow never occurs when adding operands with different signs. So of course that's saying, well, if we add 2 positive numbers and the result becomes negative, right, or if we add 2 negative numbers and the result becomes positive, right, well, yeah, of course, you know, in both of these situations, that, I mean, well, that's when overflow has occurred. Right, so try to think of examples to demonstrate this, and yeah, try using 4 bits. So if we think, well, let's say if we have 7, so of course 7 is going to be what, this, yeah, 4 plus 2 plus 1, right, then if we try to add 1 to 7, and of course, well, 1 is just going to be this, I suppose when here we can see visually quite nicely, right, of course, well, 7 plus 1, right, then it's going to go to minus 8. Because of course, well, yeah, it's going to go to this, right? Well, minus 8, and then yeah, of course, well, yeah, no 4s, no 2s, no 1s. Now let's just try some addition. So the first one we're saying is going to be 8-bit unsigned. So here then, well, 1 plus 1, well, of course, that's going to be a sum of 0, carry of 1. Again, we've got 2 1s, so sum of 0, carry of 1. Again, 2 1s, well, sum of 0, carry 1. Again, 2 1s, right, sum 0, carry 1. Right, then here we've got 3 1s, so it's going to be a sum of 1, carry the 1. Again, well, 3 1s, right, sum of 1, carry the 1. 2 1s, well, so sum 0, carry the 1. Right, and then, well, yeah, 1, then 2 zeros, right, so that's going to be a 1. So in this case, right, this is actually not going to be overflow, well, since, yeah, we don't have a carry out here. And if we actually think about this, well, yeah, I mean, okay, so let's try and calculate these values. So this first one, well, right, this one then's going to be, yeah, okay, right, this one's going to be 32. So, well, 32, right, plus 16, that's 48. Right, well, then 56, right, and 57. Right, then if we look at the next one, so what, 64, right, plus 32, right, that should be 96. Right, plus 16, that's going to be, well, 112. Right, and then, yeah, plus 416, right, 118, 119. Right, so if we add those, well, let's see what this is going to equal. So well, this is going to be 128, right, okay, since here we're using unsigned, not signed, right, therefore, of course, yeah, the most significant bit is, well, you know, positive. Right, so 128, right, plus 32, that should be 160, right, plus 16, that should be 176. And if we actually do this, well, I guess 57 plus 119, so, well, that's going to be what, 126, yeah, plus 50, yeah, okay, so this should, yeah, of course, that should be 176. Right, now, if we just try the next one, so, well, 0 plus 0 is 0, right, 1 plus 1, well, again, we said 0, right, carry 1. Right, then we've got 3 1, so it's going to be sum of 1. Yeah, and again, we'll carry the 1, right, 2 1, so sum 0, carry the 1. Right, then, okay, well, so, right, 1, then 2 zeros, right, that's, well, sum of 1. Right, then 1 plus 1 is going to be, well, sum of 0, carry the 1. Right, then it's going to be 1. And then, well, here it's just going to be 1. So if we look at this, okay, so I guess here we can actually instantly see that this is not going to cause overflow. And that's because, well, here we have different signs, yeah, since this is a signed number, right? Of course, okay, so if we say, well, this one is negative, right, then, well, yeah, then we're just plussing a positive number. So if we have different signs, right, then, of course, it can never be overflow. And the reason for that, maybe let's just go back here. The reason for that, like, yeah, okay, well, let's draw it out on a number line. And let's say, well, this is -8 here, right, this is 7 here. And, yeah, let's sort of just draw a line connecting them. Well, let's say, I don't know, okay, right, let's say we take -6. Well, if we say, well, -6 is here, right, if we add something to this, well, then it's always going to be going towards 0. Likewise, if we have, I don't know, 5, well, if we have 5 and we, yeah, okay, all right, so if we have 5 and then we add a negative number, well, then, of course, right, that's also going to be sort of, you know, going back down towards 0. So the only time we can get overflow is, well, if we have a positive and then we kind of add too much to it, that, of course, it goes outside this bounds. Right, likewise, if we have a negative, well, then, of course, yeah, we minus too much from it, and, of course, it goes outside this bounds. Whereas, yeah, if we have different signs, right, again, of course, it's always going to be getting closer to 0. Right, so then if we look at, well, BCD, binary code decimal, there's two types. So unpacked is going to use 8 bits or 1 byte to represent 1 denary digit. Right, then packed, well, it's just going to use 4 bits or 1 nibble to represent 1 denary digit. So unpacked, right, if we're looking at, well, 58, 58, I mean, of course, what we can say, well, these first 4 bits, right, this first nibble, I mean, basically it's just redundant. Likewise, of course, well, for this next digit, again, you know, just redundant. So obviously, as you can tell, right, it's just wasted space. Right, then if we look at packed BCD, well, of course, I mean, yeah, well, okay, I guess here we can say that all of the bits are going to be contributing, right? There's no redundant or wasted bits. So if we think about the advantages of, well, packed BCD, well, of course, yeah, one, right, obviously it's going to be more space efficient. We're only using half as many bits, right, 4 instead of 8 for each digit. And then this one, well, yeah, possibly it's going to be faster. And the reason I say possibly, I mean, well, like mentioned in the other video, that if you think, I mean, well, I mean, yeah, okay, so if we say, well, these bits we're just ignoring anyway. So if we're doing some calculation on, you know, like 58 or 58, right, plus, you know, 75, well, in that case, like, we're still doing the same calculation on, well, of course, you know, these 4 bits, these 4 bits. Likewise here, of course, well, yeah, these 4 bits, right, these 4 bits. So the number of bits that we're actually doing the calculation on is actually not changing. So I feel, yeah, like, again, you know, maybe it's faster, maybe it's not, right, probably depends on the hardware. Yeah, it depends on the algorithm as well. Now let's try an addition question. So we want, what, 3.14 plus 1.98. So if you remember the way we do this, well, I mean, okay, so first we just start on, you know, the rightmost digit. Of course, right, since these are the same, yeah, I guess, well, just 2 decimal places in each case, right, then, well, then, of course, we can just line them up directly. So what we're going to want, well, 4 plus 8. So if we think, well, 4 in binary is just going to be this, or 8 in binary is just going to be this. Now, if we just add those, well, that's 0, 0, right, 1, 0, of course, that's 12. Now, since 12 is bigger than 9, and remember, well, 9 is the biggest number that we can represent in one digit, you know, with BCD, then what we want to think, well, then we want to plus 6 to this. And the reason we plus 6 is because what we say that from, yeah, okay, all right, let's say, well, from values, right, 10 to 15, well, of course, yeah, I mean, well, these, you know, bit values, right, these denary values, we just can't represent. So in order to get back, well, then we have to plus 6. Now, if that doesn't make sense, I mean, I would say, yeah, watch the sort of full video where, of course, I'm going to explain that in more detail. All right, so if we plus 6 to them, well, I mean, let's just write the 6 here. So, of course, well, 6 is a 4 and a 2. Right, so, well, then what I'm going to do, I'm going to take, well, these two here, right, just, yeah, add these together. So, well, of course, well, 0 plus 0, right, 0 plus 1, right here is going to be this, right, carry the 1, and then right here. So if we also look, well, in this case, right, this is also, what is that going to be, 6, okay, right, so 16 plus 2, right, that's 18. So what we can say, okay, so actually, right, these 4 bits are fine, because, well, this is just going to be 2, and if we think, well, yeah, 4 plus 8, right, I mean, that's just going to be 12. So, I mean, yeah, here, this 2 is fine, right, but then we get this carry out. So this carry out is then going to be used, right, when we add the 9 and the 1. Right, so let's just add the 9 and the 1 now then. So, well, yeah, let's do the 1 here. Right, then we can do the 9 like this. And then, okay, remember, we also need this carry out from here. So if we have this, well, 3 1s, well, that's going to be 1. All right, carry the 1. Right, here it's going to be 1. Right, 0. And then, well, here it's going to be 1. So again, well, that's bigger than 9. That's going to be, is that 13? No, wait, 11. Yeah, okay, right, 11. So again, right, 11. So then we just need to add 6 to this again. So, right, okay, again, well, let's just add these two together. So, well, 1 plus 0, that's 1. Right here, well, that's 0, right, carry the 1. Again, 0, carry the 1. and then well, yeah, 0 carry the 1. Right, so in this case, well, of course, right, this is our next nibble. What that's just going to be a 1. And if you think about that, I guess that kind of makes sense. Well, yeah, 9 plus 1, right? Well, that of course that's just 10. But then remember, we also have this 1. Yeah, that's why we get a 1 in this position. Right, so then what we want to do again, so we want to take this carry out, and that's going to be when we're adding what 3 and 1. So let's just do that quickly. So well, 3 is going to be this. All right, well, of course, right, 1 is going to be this. Right, then, yeah, of course, well, remember this 1 up here. Right, so in this case, well, we've got 3 1s, so that's going to be a 1. Right, then there's, well, of course, carry the 1. Right, then, well, of course, here it's going to be a 0. And then, well, okay, all right, and then, yeah, sorry, right, 1 here, and then, yeah, 0 here. And then if we check that, well, that's just going to be 5. And yeah, I think, and okay, so like here's the thing with BCD, right? It's going to be really easy to check. So our answer then, what is, well, 5.12, right? 5.12, because, well, of course, right, this 1 and this 2. Now, if we actually just do this in Denary, I mean, well, let's just check that. So, well, 3.14, right, 1.98. Right, so of course, well, 4 plus 8 is going to be 2, right? Carry the 1. Well, that's going to be 11. And again, well, carry the 1, and then, yeah, that's just 5. So, I mean, that's kind of what's nice about this BCD addition, right? Even though this process is a bit tricky, yeah, checking the answer is going to be really easy. Right, and then, well, again, so, you know, here's just another practice, right? Pause the video if you want to have a go. Right, so if you've done that, well, I guess our answer should be 1.11, because if you look, well, yeah, 0.26 plus 0.85, right, of course, yeah, 1.11. Right, then if we look at, well, the advantages, disadvantages, and uses, right, the advantage, well, it means we can store base 10 decimal numbers exactly. So we said, well, I guess this is going to come in the uses, but of course, well, we can use this then for, let's say, financial transactions, because you wouldn't want a situation where if we have, I don't know, like, yeah, 0.1 plus 0.2, right, and then we said, well, that was going to equal, like, what, I don't know, was it like 0.33, okay, something like that, okay, sorry, yeah, okay, 0.3, right, 0, 0, 0, and then, you know, 4 at the end. Like, of course, if someone makes a financial transaction, well, of course, yeah, they're going to want the exact money to appear in their account. Now, obviously, in this case, actually, well, for the user, if this was a deposit, then actually, well, of course, yeah, they're going to be happy because, I mean, well, they've actually got a little bit more money. Of course, right, if they were making a payment and they actually had to pay a little bit more money, right, well, yeah, of course, you know, then they're not going to be too happy. Right, however, the disadvantage is, well, it's going to waste 6 out of 16 bits, since, well, of course, we can only represent 0 to 9, we don't represent 10 to 15. Right, also, well, complex circuitry for arithmetic, so well, addition, subtraction. I think actually those are not too bad, but I think multiplication, division, yeah, they get super complex apparently. I think, as you can probably imagine. And then, well, yeah, okay, like, because of this more complex circuitry, right, therefore it's going to be slower. Right, there's some of the use cases, well, digital watches, timers, stopwatches, alarms. So anywhere, like, if we only need to represent each digit independently, right, then I guess we can use BCD. Right, also scientific equipment, so, and, well, of course, I mean, the reason for this is because here, since we can represent base 10 decimal numbers exactly, like, if we want to exactly represent, you know, 0.3, well, yeah, if we want to exactly represent, I don't know, 0.529, you know, obviously something like this, right, then, of course, we can use BCD to represent it down to this number of decimal places. So things like, well, voltmeters, oscilloscopes, right, and also, well, financial values, right, as mentioned. Right, then if we look at text, right, or the internal coding of text, yeah, I always kind of, you know, I say that wrong, yeah, like a tongue twister. Right, so as mentioned, well, numbers, images, video, sounds, right, text, programs, right, yeah, of course, well, everything is just binary. Right, therefore, we need a representation of characters in binary, and, well, these can be ASCII and later Unicode, and, of course, yeah, these are called character sets. So the definition of a character set, well, it's a collection of characters whereby each character is represented with a unique binary code. And in the exam, right, if you don't say unique, right, I mean, they actually won't accept it. So yeah, if you just say binary code, I mean, well, maybe you'll get 1 mark, but yeah, in order to get both marks, right, well, of course, you have to say unique. Right, then if we look at, okay, all right, so, all right, yeah, okay, maybe I forgot to mention ASCII. So ASCII, well, there's 2 types, right? There's going to be a 7-bit, which is standard ASCII, and of course, well, yeah, 7-bit ASCII, that's going to represent 128 different characters. Right, there's also extended ASCII, which is, 256 characters, because, well, of course, extended ASCII is 2 to the power of 8, okay, yeah, 8 bits per character, and, well, standard ASCII, well, 7 bits per character, 2 to the power of 7, right, 128. And if we think, well, I mean, ASCII, basically, this can just represent the characters on your keyboard, yeah, it can't really represent, well, again, let's say other languages, well, Chinese, Arabic, yeah, obviously, other languages with like much more than 256 different characters. Right, so to get around this then, well, this is why Unicode was introduced, yeah, to have more than 256 characters. And Unicode can represent all characters in every language, yeah, all the mathematical, scientific symbols, right, all the emojis, even things like hieroglyphics, right, these kind of ancient languages. Right, currently there's, well, 144,000 characters, and I think as mentioned in the other video, like, probably this has increased since, well, every year they're always, adding new emojis or adding extra stuff. And yeah, I guess what in total has room for over 1.1 million. Then if we just look at this, yeah, I guess this table, so this is just the UTF-8, right, the 1 to 4 byte formats. So if we have a single byte character, well, then it's going to, then it's going to start with a 0, well, then just have, yeah, kind of 7, remaining bits. Right, if we've got a 2 byte character, well, of course, right, then it's going to start, well, 110, right, for the first byte, and then the second byte here, right, it's just going to start 10. And of course, the reason it needs this fixed format is because, well, if you just have, a long string of bits, like, if we're using a variable length encoding like UTF-8, right, then, well, yeah, okay, all right, let's say the decoder or the program, the decoder is not going to know, when this character starts or, when this character ends, for example. Because, well, of course, like if you have sort of A, B, C, D, well, in this case, it's going to be simple. Of course, well, this is going to use 8 bits, this is going to use 8 bits, right, 8 bits, 8 bits. But if you have, I don't know, some like smiley face emoji, well, of course, well, and let's say A, or then, I don't know, let's say some like Arabic symbol or something. Well, like this one is probably going to use 4 bytes. Yeah, the A is just going to use 1 byte. I mean, maybe the Arabic symbol, maybe uses 2 bytes. So, of course, yeah, because they're all different lengths, well, that's why we need a, sort of bit pattern, yeah, to signify, well, the length of this character, right, when one starts, when, yeah, and obviously when one ends. Right, so to have a summary of that, yeah, I guess not too much. Well, if we say the ASCII values, well, right, 0. So of course, well, yeah, the number 0, the character 0, it's going to be 48 in ASCII. Right, if we look at uppercase A, big A, right, that's going to be 65, and well, lowercase a, 97. And of course, if you remember, what the difference is going to be plus 32, right? So to go from uppercase to lowercase, we plus 32. Obviously, well, to go the other way, right, from lowercase to uppercase, well, of course, just minus 32. And if you remember that, what in hexadecimal, this is going to be a difference of 20. And the reason for that is because, well, yeah, I know, okay, let's just say this. Yeah, okay. Alright, so if we say, well, here, bit 6. Now, to go from uppercase to lowercase, well, of course, we just have to change this bit 6. Right, so from uppercase, okay, right, if this is uppercase, well, bit 6 is always going to be 0. But then if we want to convert that into the corresponding lowercase, so again, for example, big A into small a, well, like, okay, all right, so yeah, all of these other bits are going to stay the same. And then since we're just plussing 32, well, of course, bit 6 has the value 32, right, therefore, yeah, that just goes to a 1. Of course, right, well, of course, yeah, if we're going the other way, right, from a lowercase letter to an uppercase letter, well, of course, right, this 1 is just, yeah, just going to become 0. And of course, that's why it's fast, right, just to convert between uppercase and lowercase. Right, so just a quick recap. Well, ASCII is going to be older, right? 2 versions: standard 7-bit ASCII, extended 8-bit ASCII, and can represent 128 and 256 characters respectively. Right, then Unicode, well, can represent all characters, uses between 1 and 4 bytes per character. And if you remember, well, UTF-16 is going to be fixed length, always uses 16. UTF-32, again, fixed length, always uses 32. But then UTF-8, right, that was going to be the variable length, right, that uses between 1 and 4 bytes per character. Right, so then if we move on to images, well, bitmaps, they're going to consist of individual picture elements, of course, well, more commonly known as pixels. Of course, yeah, well, the PI here, obviously, yeah, the ELS here, and I guess, well, this X just kind of, yeah, randomly thrown in. Right, so pixel is going to be the smallest unit of an image or graphic, yeah, or screen, right, that can be displayed on digital devices. So, I mean, if you think, well, pixel, like in most cases, well, it's just going to be, yeah, the sort of, what kind of individual square. Right, each pixel has a color value, right, it could be RGB, right, it could be black and white, yeah, it could be something else, well, I think as mentioned before, what's CMYK, right, so well, cyan, magenta, yellow, and well, key, which is black, and I mean, cyan, well, that's a light blue, right, magenta, I mean, basically pink, well, of course, yeah, yellow and black. Right, so for example, well, this RGB value, well, of course, right, 255 red, 0 green, 0 blue, because, well, yeah, FF is 255. Right, the resolution, this is the number of pixels in the image, right, i.e. a higher resolution equals higher quality. However, of course, also, right, larger file size. Right, bitmaps can be considered a 2D array, right, or matrix, I guess grid, right, of pixels. Right, the bit depth, color depth, this is the number of bits used to represent right, a color for each pixel. So if we say, well, the bit depth is, for example, 8, well, this means, each pixel is using 8 bits. And of course, well, bit depth and color depth, well, yeah, they're just interchangeable, right? It means the same thing. Right, then just continued. So purely black and white image only needs a bit depth of 1. And when I say purely black and white, so what I'm saying is like, okay, literally, right, if you only have either black or you have white. Now, some people, when you hear black and white, well, of course, they always think, well, grey and, like, obviously variations. Well, different shades. But yeah, in this case, it's saying, well, I guess either like 100% black, right, or 100% white. It's not just talking about an image with no color, right? So bitmaps, well, they're going to be good for photos, or let's say sort of complex like render digital artwork. Things like this background here. If you think, right, something you would make in Photoshop, right? If you're making some complex, 3D thing with like explosions and various lighting effects or all this complex stuff. That's really where you're going to want to use a bitmap, right? Just pixels. Right, and as mentioned, well, increasing the color depth, right, or, well, again, right, so color depth or bit depth, right, or increasing the resolution. Well, the good thing is going to increase the quality. However, of course, the bad thing, right, is going to increase the file size. Right, then, well, if we look at files, images and others, so I guess, some examples of images, JPEG, PNG, obviously, MP3 sound, right, MP4 video, EXE, right, executable, right, program, obviously, doc, like a Word document, just a sort of, written document, right, PDF, I think maybe like portable document format, obviously, kind of similar to a doc, right, just, a little bit more advanced features, obviously, GIF, so actually, a GIF, it can also be a static image, but I guess, most people are more familiar with, of course, the animated GIFs. Right, so all of these are going to contain headers. We say, a header is just additional information at the start of the file that, let's say it defines metadata. If you remember, metadata, we say, that's data about data. So, in this case, right, it's going to be data about the file. Right, some files also include, a trailer or footer. That's going to be metadata at the end of the file. So let's see an example of some of the things kind of included in an image header. So if you remember, one's going to be the file type, and that's going to be called the magic bytes. Now, if you actually want to see a list of these magic bytes, I think, just type in magic bytes Wikipedia, there's going to be a list. And I think actually on Wikipedia they call it like file signature, or list of file signatures. Right, that's the Wikipedia article. So, for example, I think we mentioned if we have a JPEG, so I can't remember exactly, but I think for some specific version of JPEG, right, all of them were going to start FF. Then maybe it was like F3 or maybe F8, I can't remember. All right, then there's another, there's going to be another byte. And the reason they start with this is because, let's say you could have an image. Now, one, maybe the image just has no extension, right? Just, let's say you just have a face, right, smiley face. Right, so if here there's no extension, well then of course what's that? Is it going to be a text file? Is it going to be a document? Right? Is it an executable? Who knows? But you could also have it where let's say someone mistakenly saves it as face.png, right? But it's actually a JPEG. Now if you say that, right? If you say right, let's say that this particular version of JPEG is going to start with these these 3 bytes, or 6 hexadecimal characters. Then of course, the image decoder can obviously then recognize that this is a JPEG, right? It's not a PNG, and of course interpret that accordingly. Alright, so some of the other things mentioned, there's going to be the resolution, defined in the header, also the bit depth, right, and other things like the title, description, right, camera, maybe the geolocation, right, time taken, program, etc. Now, I think in the exam, I would say definitely mention these two, maybe also the file type as well. Now, if you think, I guess similar to kind of text, where if we say, let's say if we're using Unicode or UTF-8, then of course we need to know, when does one character start, and obviously, when does that character end, when does the next character start? It's kind of similar here, where we need to know, so I guess we need to know the resolution because, we need, let's say we have pixel 1, pixel 2, pixel 3, pixel 4. Now, if, for example, we've got, a 1x4 image, well, then of course what these are going to do, yeah, they're going to be displayed all in one row, right? If in contrast, of course, well, we could have a 2 by 2 image, right? We could have a 4 by 1 image. So of course, well, again, right, let's say the decoder needs to know, well, yeah, okay, which row is this pixel on? Likewise, yeah, which row is this pixel on? Right, likewise the bit depth. Now, if you've just got a sequence of bits, yeah, I don't know, whatever. Well, let's say if we got, I don't know, say a bit depth of 4. Well, then of course it's going to realize, well, okay, this, these are the first pixel. All right, then of course, well, yeah, this is going to be the next pixel. This is going to be the next pixel. So again, that's going to be how it just kind of separates out, pixel by pixel. Yeah, probably a bad explanation, but I mean, I think hopefully people can understand that. Right, then if we want to calculate the image size, so let's try a question here, no calculator. Right, an RGB image, 4096 by 512, right, save using a bit depth of 32. Right, calculate the file size of the image, right, in Mebi bytes. So here, well, yeah, okay, right, if we think the way to do this, well, basically you just want to write everything out and then just try to simplify, right, based on the powers. So let's go 4096. Right, then if we try, times, right, 512, well then, right, times 32. So of course, this is going to be how many pixels, right? Then we say, each pixel is, 32 bits. Right, then if we want to convert to Mebi bytes, well, first we just need to divide by 8. Right, then what Mebi is going to be, 1024 squared. So yeah, let's go time, okay, 1024, times 1024. Now let's think about what we can simplify. So I think maybe this 32, right, so this 32 and 8, well, I guess this can just become 4, right, and then we can just cancel the 8. Right, then if we do, let's say, the 4096 divided by the 1024, well, that's just going to be 4. So yeah, this becomes 4, and then here we just cancel this. Right, then if we do 512 divided by 1024, well, that's going to be 0.5. So if I just write that out again, well, it's going to be 4 times 0.5, right, times 4. And then, yeah, well, again, then, I think here we've cancelled everything, so just, yeah, over 1. And I suppose if we do that, that's just going to be 8, because, yeah, 4 times 0.5 is 2, right, times 4. Yeah, that's just going to be 8. Right, so therefore our final answer is just going to be 8 Mebi bytes. Right, then if we look at vectors, so, yeah, I guess, okay, so vectors, well, of course, it's just going to be the second type of image. Right, so rather than being defined in terms of pixels, they're defined in terms of, shapes, coordinates, properties, attributes. Right, for example, you can create different shapes, ellipses, right, circle, oval, right, rectangle, square, right, polygon, line, right, text, etc. Right, many different things. Right, the main advantage is, they're going to have a smaller file size for certain types of images. So things like simple logos, right, just comprised of simple shapes. Right, also the other advantage is, we can scale to any size, right, either bigger or smaller, right, without reducing image quality. Then if we look at the terminology, and I'm just going to show all of them because, here we have an example. Right, so an element or drawing object, that's going to be an individual component of a vector image. So, I mean, in most cases, that's going to be a shape, right, although, I mean, this could also be text. I mean, it could also be things like, I think you can do, gradients, right, which you can define externally, right, there's also other things. But I guess, okay, kind of like the simple one is just going to be, different shapes. Right, then it's going to be a drawing list, so that's the collection of all elements. So if we see here, the drawing list is just 2 elements, the rectangle and then the line. Right, the attributes, properties, right, additional information about an element. So here we see the x position, right, we see the width, we see the height, right, then also the fill color, and everything F00, RGB, right, just red. Right, then we see the value, so that's the value of an attribute or property. So I guess here what we're saying, the x attribute has a value of 120. So I guess, just 120 pixels, right, from the left. Likewise, of course, the width, right, 100 pixels. And of course, right, etc. for those other two. And if you think about the line, of course, we've got a starting x position, starting y position, and obviously ending x position, ending y position. And then, this stroke, this is just going to be the outline color. Right, so if we see here, the right is going to be the vector image, and as we see, right, no matter how much you zoom, right, or resize, then the image quality never decreases. And as mentioned, of course, the file size also never increases. So even if we want to make an image, I don't know, let's say 1,000 or is that 1,000,000? Yeah, okay. So let's say we want a vector that's sort of 1,000,000 by 1,000,000, right? If if we're sort of talking in pixel sizes, then in that case, of course, the file size is just going to stay the same. And the reason for that is, since the elements, properties are defined mathematically, then we can just multiply by a scale factor. So for example, if we go back, let's say for example, if we want to make this image like 10 times bigger, well then we can just multiply this x1 by 10, right, y1 by 10, right, this by 10, this by 10. Of course, yeah, obviously, well, the width multiplied by 10, right, the height multiplied by 10, right, etc. Alright, so yeah, then if we move on to sound, right, sound is going to be analog, right, i.e. various or varying continuous signal. Right, computers can only understand digital or binary data, so sound has to be quantized, and that means rounded to a discrete level. So if we see this one, well, this is going to be our analog signal, right, nice and smooth. But then if we see our digital signal, well, here I guess, well, this is going to be one quantization level. Well, that's another quantization level, right, another one, so other ones here. So of course, well, yeah, because these have to be rounded to these kind of discrete quantization levels, right, that's why we get this, stepped pattern. And of course, yeah, this is going to be lower quality. Right, so if we look at some key definitions, right, sample, well, that's a measurement of the amplitude of the sound at a given instance. So if we see here, where's the pen? Alright, so okay, let's say here, I don't know, maybe this is our first sample. Then let's say we've got a sampling resolution, a sampling rate. Now, let's say this is in seconds. Now, if we have a sampling rate of, well, let's say 2 hertz, right, 2 samples per second, then I guess what we're going to take another sample here, right, we're going to take what, another sample here, right, another sample here, right, another sample here, yeah, of course, etc. And I suppose, I mean, well, of course, if we're doing that, what we're saying is going to be the amplitude. So where, okay, right, here's the pen. So of course, well, I mean, yeah, that's going to be our value at this time. Right, our value at this time is going to be, well, this black line. Since, again, like if we think, well, here, right, these are going to be our quantization levels, right, these black lines. Right, so the sampling resolution of bit depth, this is the number of bits per sample. So of course, we're increasing the sampling resolution bit depth. Well, that's going to, I mean, well, one, it's going to make the sound more accurate, right? More accurate compared to the original analog signal. However, of course, well, the file size is going to increase. Right, then my sampling rate or sampling frequency, that's the number of samples per unit time, right, e.g. per second. Which, yeah, I guess we can see here, right, if we look at this. Right, so as mentioned then, right, if we increase, the sampling rate or sampling frequency, likewise, if we increase, the bit depth or sampling resolution, then of course, we're just going to get more and more accurate. So, yeah, of course, when we have the highest, therefore, therefore we get, the most accurate. Right, if we have a low sampling rate, right, a low bit depth, right, therefore we get something that's, not very accurate. Right, so let's think what would be the problem if we sampled at too low a frequency. And hopefully you can realise, of course we wouldn't accurately capture the waveform. Right, however, if we sampled at too high a frequency, here we can say the waveform would be accurate, but the file size would become unnecessarily large. And, I mean, if you remember that, that was where something called Nyquist theorem came in. Okay, hang on, right, alright, so, NYQ, like this. Now, actually, this is not on the syllabus, but, like, if you just remember, they said that, well, in order to accurately capture the waveform, we have to sample sort of greater than or equal 2 times the maximum frequency. Right, that's just what he said. Then let's try and go through some of the key terms, right? So the first one, sample. That's going to be a measurement of the amplitude at a given time. Right, then sampling rate, frequency, and in fact, right, I'm just going to show all of them. So sampling rate, frequency, that's going to be the number of samples taken, e.g. per second or per unit time. Right, the sampling resolution bit depth, that's the number of bits, let's say the number of bits used, per sample, right, for each sample. Right, the amplitude, of course, that's going to be the volume, right, the distance, I guess kind of what the distance up the x-axis, basically. Right, the quantization, so that's the process of converting the continuous analog signal into the, discrete digital signal. And of course, what we say, the signal has to be converted to the, Alright, so the signal has to be converted to one of the quantization levels. So if, for example, I don't know, right, maybe this is 0, this is 1, this is 2, this is 3. Now, if we have some value, let's say here, like 0.8. Well, of course, we can't actually store 0.8 in this case, right? That's going to have to be rounded up to 1. Let's say in the next one, I don't know, maybe we have 2.2. Well, of course, 2.2 is going to have to be rounded down to 2. Therefore, in order to join them, right, it's going to be this stepped pattern. Alright, and then I suppose, here are just the answers. Right then, well, the formula for calculating an audio track's file size, so what that's going to be the sampling rate, right, how many samples per second, right, then multiplied by the sampling resolution, so well, the size of each sample, right, so that's going to tell us the size for 1 second. Well, of course, right, then we just want to multiply by the duration, right, and of course, well, then we need to multiply by the channels, because, well, maybe we have, you know, a left and right channel, right, maybe we have more than that. Yeah, so that should be all of those. Right then here, so sound in the real world is, well, this is going to be analog, right, but it has to be converted to, well, digital, right, to be stored on a device such as a phone or computer. Right then, explain what happens to the audio quality and file size when the sampling resolution and sampling rate or frequency are, well, I guess, yeah, are increased. So, of course, well, we say the quality is going to increase, you know, right, if the, well, sampling resolution or bit depth, yeah, or sampling rate frequency, you know, increased. However, the file size also increases. Now, obviously, yeah, okay, well, obviously, right, I mean, okay, let's say the quality increasing is obviously a good thing, right? The file size increasing, well, yeah, obviously a bad thing. Yeah, and I suppose, well, here's just a more detailed explanation, right, if you want to read that. Right, so video, I think let's skip this. I mean, progressive, well, it just shows the video frames at once, right? Interlace, right, shows only, yeah, I guess only half of the lines, right, half of the rows. And the reason why I'm skipping this, well, this is actually not on the syllabus. Now, if you want to have a go at this calculation, right, just pause the video. So yeah, how many Mebi bytes would each second of video consume? And actually, you know, for calculating video, right, it's just going to be what the same as an image. But then you're just going to think, well, then you want to multiply by how many frames per second, and then obviously, like audio, right, of course, where you also have to multiply by what the duration. Right, so I guess, yeah, if you do that, right, well, that's going to be your answer. Right, so I think the final thing is going to be compression. Right, let's look at the benefits. Well, one's going to be faster transmission, right, uploads, downloads, copying. Right, two, it's going to save space on secondary storage, right, hard drives, SSDs, I guess, yeah, USBs, right, if you're looking for backup as well. Right, also you can send as an email or file attachment if it's otherwise too big. So a lot of, I guess, well, a lot of email programs especially, they have, let's say, like a 25, I don't know if it's going to be Mebi bytes, or yeah, maybe, I know, or yeah, maybe just megabytes. But a lot of them are going to have limits, right? And of course, like if the file is too big, it's not going to let you send, right? Therefore, if you can compress it, maybe you can compress it so it's under that limit, right? And yeah, therefore you can of course send it. Right, it's also going to use less bandwidth, right? E.g., if you have a monthly phone contract with 20 gigabytes per month, right? Then of course you don't want to be watching some, you know, gigantic video, right? That's using up all your data. And then, well, let's think, right? Why don't we compress everything, right? E.g., the entire hard drive, you know, if we get all of these advantages. And of course, well, the reason is that, well, I mean, when we're decompressing, you know, decompressing is actually going to take time. Like if you wanted to, I don't know, okay, right, let's say you want to search your entire hard drive, you know, for, I don't know, searching some file you were just editing. Well, as you were searching, you'd have to decompress every single file on your hard drive. And of course, yeah, that's going to take, you know, a ridiculously long time. Right, so let's look at the two different categories, right, lossy and lossless compression, and I suppose, yeah, these are going to be what umbrella terms for, yeah, different algorithms, different methods, right, different techniques. Right, so lossy, well, here, as the name suggests, data is lost, right, i.e. quality is reduced and can't be recovered. Well, lossless, again, right, as the name suggests, data isn't lost, right, quality stays the same and the original can be reconstructed perfectly, right, however, the slight disadvantage, right, of course, where it can't be compressed as much. Right, so the first one, well, run length encoding, this is where we say if we have the same color pixel consecutively, right, then we can store it in this format. So we say the number of consecutive cells with the same color, right, then we say the color value. And of course, well, yeah, okay, like, of course, if this was a real image, right, both of these are going to be in binary. So if we look at this Mario image, well, we can say, well, maybe we have 1,000 blue first, because, well, of course, yeah, this, you know, 1,000 blue going along this top row. Now, actually, I suppose, well, of course, yeah, I mean, here's, well, this row 1, but then, you know, also row 2 is also, you know, blue, right, row 3 is also blue. Then obviously, well, eventually we're going to get to about here, which we're, which of course, well, we're going to see like a little bit of black, right, for the stroke of the cloud, right, then probably about 10 white for, yeah, kind of the inside of the cloud, right, more black, right, more blue, yeah, etc. So again, you know, hopefully people are familiar with this, right, if they're not, well, probably, yeah, I guess either watch the, you know, original video, yeah, or, you know, look in the book. Right, so let's also think, well, will run length encoding work well with photos? And of course the answer is going to be no. And the reason for that is, well, very few pixels will be, very few consecutive pixels will be identical. So we might have, for example, this, which, well, of course, yeah, this is going to be white. However, we say, right, the next pixel is actually this. So even though to the human eye it's going to look the same, obviously, well, to the computer it's actually going to be a different value. Right, therefore, because they're different, well, then we can't use run length encoding. So if we think about lossy, well, we just want to think about the formula for calculating an image's file size, right? Then we can just reduce any of these. So if you remember the formula, well, it's just resolution times the color depth. Right, therefore, if we reduce either the resolution or the color depth, well, of course, that's just gonna reduce the image size. Right, then if we think, well, lossless audio compression, well, this is just going to be Huffman coding, and let's look at this later, right, when we talk about text. And yeah, as mentioned, well, it was originally developed for text compression, but since all files are just binary, well, then of course, yeah, we can also use Huffman coding for other files, right? If the, I guess if the kind of, I don't want to say formats, like maybe the pattern, if you get the same sort of patterns, right, in the file, that makes it that, Huffman coding can compress it well. And if we think about, like, okay, so where Huffman coding works well is if we have some values that are common, and then, so I guess it's kind of this, right? This was the chart. So this would be the date. Right, this is the frequency. No, all right, sorry. Yeah, okay, right. So this is the data here, right? This is the frequency on this axis. So what we're saying is, well, if we have some data that's, super common, and then actually the data that is not common is actually, well, I guess, quite rare. We don't really have much of this, right? If we have this kind of relationship, right, then Huffman coding is quite good. If we have something like this where we have kind of all data is equally common, right, then Huffman coding is actually not going to work as well. Because if you remember, well, of course, here we're going to use, right, shorter bit patterns for these common ones, right? Then, of course, longer bit patterns for these, less common ones. But if everything is, just as common, well, I mean, obviously some of them are going to be, shorter bit patterns. But then in this case, right, this is actually going to use longer bit patterns, right, compared with if we just represented it in ASCII or Unicode directly. So maybe that makes sense. Right, but if we look at lossy audio compression, well, one, we can remove frequencies and low amplitudes that are inaudible, right, so can't be heard, well, to the human ear. Right, so i.e., well, quiet sounds, right, and also very high or very low frequencies. So what things outside of the human hearing range of 20 to 20,000 hertz. Anything less than that, anything greater than that, right, of course, we can just remove. Right, we can also start with an average amplitude, then store the differences rather than the actual value. So if, do we have an example? Yeah, okay, so for example, let's say if we start at 50 decibels and we want to store 50.1 and 49.9, then we could just say, well, of course, this is our average 50. And then instead of saying 50.1, okay, we can just store that as, well, plus 0.1. Likewise, well, 49.9, of course, store that as, well, minus 0.1. And of course, storing these numbers is going to use fewer bits, right, compared with, right, storing these numbers. Right, then again for lossy, well, we just want to think about the formula. So the formula, what the sampling rate multiplied by sampling resolution, of course, well, the sampling rate, again, bit depth, right, sampling rate is the sampling frequency, right, the sampling resolution, all right, this is also the bit depth, obviously, multiplied by the channels, right, so, well, left, right, I guess kind of, well, you can also get surround sound, that has, more than 2 channels, right, also times the duration, so any of those we can make smaller. And as mentioned in the other video, well, usually the channels will just be 1 in the exam, so of course you can't reduce from 1 channel to 0 channels, right? Otherwise there's just going to be no sound. Likewise, reducing the duration, like, well, either you're going to be speeding up the sound, right, which is, probably not desirable, like, or you're just going to be, cutting off the end of the sound, which, again, right, probably also not desirable. So I think just saying these, right, okay, well, either reduce the sampling rate, right, or reduce the sampling resolution. And for example, right, if we half the sampling rate, right, then of course we're going to half the file size. Right, then video, well, if you want to read this, I guess, you can read it, but I'm going to skip because, well, this is not on the syllabus. Right, and then, well, lossy again, right, just think of the formula. Of course, just reduce any of those. Right, so then if we look at Huffman coding, and maybe this is the last thing. So, right, if we have the input text hello world, well, first we just want to create a frequency table of the number of occurrences of each character, and this is going to be case sensitive. So of course when it says case sensitive, well, this is saying what big H, that's going to be not equal, right, to small h. And I suppose, right, since it's a character, let's put it in single quotes. Right, then once we've done that, well, then we're going to assign Huffman codes to letters with the most common letters having the shortest Huffman codes. So, right, okay, well, of course, this is step 2. So if we were creating the frequency table, I guess, well, the frequency table of big H, well, in fact, right, maybe let's just do it here. So, of course, what big H has only 1. Right, then look, well, if we look at E, right, so E is also only 1. Right, then if we look at L, okay, so, right, so L actually has 3, right, of course, yeah, 3 occurrences. Right, so of course we're just going to do that, right, for each character. And we say what the common letters again have the shortest Huffman codes. Right, that's why we see what L here is number 1. Right, therefore, of course, yeah, it just has the right Huffman code with 2 bits. Right, whereas if we look at E, and also H, right, they only have 1 occurrence. Right, therefore they're using 4 bits. Right, then we want to replace each letter with the corresponding code. So if we see H, well, of course, what H is hang on, right, okay, here we go. So of course, what 3 1s then a 0. Right, then if we see E, what E is just going to be 4 1s. Right, L, well, just 1 0. And yeah, if we do that, all right, then we get this here. And then, well, remember, of course, if you want to have a go at this online, just type in like Huffman coding online, right, and then there's going to be various websites which you can, play around with this. Right, the important thing to note, well, the generated Huffman codes are chosen, so there's only one possible decoding. Right, then if we're looking at the decoding process, so here we have the bits, right, then, then of course we just want to convert to the original text, or the original data. So we're going to start on the left and find the character each sequence corresponds to. So let's say here, well, we start at 0. So well, of course, I mean 0. Yeah, okay. So I guess it could be this one, right? Yeah, it could also be O, right? It could be a space, right? And yeah, also it could be an X, right? But well, then if we go to 1, so let's see. Well, yeah. So okay. So I guess this one is still valid, right? 0 1. But then if we look at O, well, of course, right, O is going to be invalid, right? We can discount that. Right, space. Yeah, okay, space also invalid, right, but then X will also 0 1, right, possibly this. Right, but then if we look at the next one, well, 0 1 1. So 0 1 1, okay, right, here we go, right, 0 1 1 we're going to see is L. So yeah, let's just write that. Alright, then if we're on the next one, so now we're on this 0. Again, we can do the same thing. Well, let's go, right, 0 0. And let's just try and spot these quickly. So I think if we go here, right, well, 0 0 0. Yeah, that's just going to be this O. Alright, then of course, well, we're starting on this 1, right, looking for the next one. Right, then if you do that for the whole thing, then yeah, you should just get lossless text, or yeah, well, I guess yeah, lossless text compression, right, although of course yeah, that's going to be too long. Right, and then we said yeah, this can be used for audio, and the reason is because well, some amplitudes will appear repeatedly, which yeah, I guess you can see here, right in this just little graphic. Right, so let's say we then just want to have a recap, right, list the lossy and lossless compression methods for text, images, and audio. So for text, well, we can use Huffman coding, right? Yeah, I mean, in the exam, they often mention run length encoding, although realistically, I would say you can't really use run length encoding for text. Since, I mean, okay, like, well, maybe someone does, sort of AAA. Like, yeah, maybe someone types that just as, I know, some, like, yeah, if they're sort of, like, laughing or something. But, like, yeah, I mean, okay, or let's say in normal text, people don't actually do that. And the thing is, when you think, okay, you've also got to store the count. So if you just want to store, well, let's say ABC. Now, instead of just storing, let's say the ASCII values, well, this time, we've also got to store what, 1A, right? Well, then 1B, yeah, 1C. So, of course, well, in this case, we're actually going to double the size, right? If we're saying that, well, this is 1 byte for the number, then also, 1 byte for the letter. So that, I mean, yeah, that's the thing with run length encoding, right? Sometimes this can actually make the file bigger, right? If the file can be compressed well with run length encoding. Right, then images. So, well, yeah, okay, right. If we're talking about lossy, well, then we can just reduce the resolution, right? Also, well, reduce the bit depth, color depth. Right, then for lossless, well, run length encoding. And the reason this is lossless, well, because, well, okay, I mean, well, yeah, let's just say this, our text example. Of course, if we have this, right, 1A, 1B, 1C, well, then, of course, we can just, directly go, well, of course, right, that must be ABC, right, since, well, yeah, 1A, 1B, 1C. Same for images. Like, if we have, what, 5 red, I know, 10 pink, like 5 orange, well, then, of course, yeah, we can reconstruct that perfectly. And if we just think, like, why does text only have lossless? And the reason for that is, well, we don't really want to have lossy for text because, well, otherwise you're just going to lose some of the, well, yeah, I mean, of course you're going to lose the data. Now, you wouldn't want to be sending a message to someone and, like, half of the letters just become missing. Since, of course, well, in that case, right, they're probably not going to understand what you're saying. Right, then for audio, well, again, just, yeah, okay, so I guess here, well, just reducing anything in the formula, right, so the sampling rate, yeah, well, also called sampling frequency, well, of course, yeah, the resolution, right, or the bit depth. Yeah, and well, the number of channels if it's more than 1. Of course, if the number of channels is 1, well, then we can't reduce it. Right, in terms of lossless, and Yeah, okay, so like really, this is not actually lossless. Like from a human's perspective, it's lossless because, well, of course they can't hear it. But from the actual, well, yeah, okay, I mean, from the sort of digital files perspective, then of course, if we're actually removing these amplitudes, well, yeah, low amplitudes, or removing these, yeah, kind of what inaudible frequencies, then this means we actually won't be able to represent the original perfectly. Although, I mean, since people can't actually hear those sounds anyway, um, yeah, so honestly, okay, right, these should actually be lossy, to be honest. And then, well, Huffman coding, right, that's going to be the only lossless. So again, all right, yeah, that's going to be a mistake, right? They should be lossy. Right then, well, explain how run length encoding work. I mean, you can have a go at this if you want. Well, it's just going to be what the number of consecutive pixels, and then of course, well, just the value. So yeah, just a count, right? Then the actual RGB value. Right, and then Huffman coding, what we're just going to make the frequency table of the most common characters. Then we're going to replace the most common characters with the shortest Huffman codes. Right, of course, yeah, the longer, the less frequent characters have the longer Huffman codes. Right, then we're just going to go through character by character, replacing each character with the corresponding, generated Huffman code. Yeah, and again, right, the thing to note, well, right, they're going to generate a Huffman tree, so there's only one possible decoding. Right, guys, so I think, yeah, that's actually everything in Unit 1. Now, as mentioned, well, here I'm just going to show this kind of, chapter overview again, right, unit overview. I would say read this, right, make sure you're confident with all of this. And I'm also going to go next to the syllabus here. So here, well, yeah, all right, so let's look at the syllabus checklist again. Okay, use this as a checklist, right, make sure you know everything. Right, so the first part, I mean, I'm not going to read it because honestly that's a huge amount, but yeah, I mean, we have covered all of this, right, so pause the video, right, have a read. And this is going to be all the sort of binary, right, and well, text and things. Right, then I think this one's going to be, yeah, the multimedia, right, so just images, actually. Again, right, pause it, yeah, make sure you know all of this. Right, so of course, well, this one just sound, right, obviously not as much. And then I guess, right, yeah, finally, compression. Alright guys, so yeah, I think for that video, well, that's everything. Now, hopefully this video is useful. As always, right, if anything doesn't make sense, well, I mean, yeah, probably that's been just over an hour, right, maybe an hour and 15. I mean, as mentioned, I think Unit 1 is probably the biggest chapter, or yeah, one of the biggest chapters. So probably this should be like 12 hours of class time, right? Therefore, of course, in 1 hour, yeah, of course, it's going to be impossible to explain everything. So if you haven't sort of understood everything, well, right, then of course you can watch the other videos. You can also use the book, right? Use Google, yeah, use ChatGPT, right? Yeah, whatever you want to use. Of course, if you have any questions, right, you can also ask in the comments. And yeah, hopefully see you in the next videos, right, when I'll start looking at Unit 2.